Hi everyone, I'm Colin. This is a video tutorial on demonstrating the use of proportional control in Simulink to balance a LEGO Mindstorm designed inverted pendulum. Here's the setup of the inverted pendulum. On the right is the LEGO Mindstorm pendulum. A clamp is used at the bottom to prevent too much shaking. At the base of the pendulum is the motor, which pivots and controls the pendulum arm, as well as records the angle of the arm from a motor encoder. The arm is used for the rotation of the pendulum. At the top of the pendulum is the load, which acts as a weight to increase the torque of the pendulum. The motor is connected to the NXT brick via the NXT cable in port A. The NXT brick powers the system, as well as controls it. Connecting the NXT brick to the host computer is the USB cable, which has the purpose of uploading the Simulink model to the NXT brick. To sample and record the encoder data onto the host computer, a Bluetooth connection is used. The host computer is used to design the Simulink model as well as interpret the encoder data on Matlab. Now that everything is connected, the Simulink model for the inverted pendulum can be created using the Access software. To open up the Access software, type Access into the Matlab command window. Now, click on the LEGO Lab button in the Access software window. Next, choose a position control experiment. Make sure to change the simulation time to last long enough for the experiment. Click Open Model. For the inverted pendulum experiment, this Simulink model will need to be altered. Change the step block to a pulse generator block and add a motor gain block inside the open loop. The pulse generator block is responsible for creating a pulse train as an input signal to the system. To the right is the transfer delay block, which creates a delay to the input signal of 1 second for the purpose of allowing the motor encoder to initialize. In the open loop transfer function, there are two gain blocks, as well as the motor gain block. They are used to convert the degrees of the encoder to radians, voltage to voltage percentage, and to multiply the system by the motor gain. The PID controller follows next, with the purpose of controlling the pendulum. The values of the controller are P equal to 2.2048, I equal to 0, and D equal to 0. The value of P equal to 2.2048 can be calculated through Matlab computation of the closed loop transfer function for this particular pendulum. Next is the saturation block, which is used to control the power percentage of the motor. The motor block then receives the instructions from the previous blocks and relays this into the NXT motor for actuation. The encoder block acts as the sensor of the system, constantly receiving a new angle and updating the system based on this new angle. A comparison is then made between the input blocks and the sensor block, and the result allows for an adjustment to the actuation controls. The last two blocks are the output block and the input block. The output block is connected to the encoder block so that it can collect the response of the system and transfer it to Matlab as an array. The input block is connected before the summation so that only the pulse generator data is transferred into Matlab as an array. Now that both the physical setup and the Simulink model are ready, the experiment can begin. To proceed, simply run the Simulink model and observe. If the plot to figure button is clicked, the results can be observed on a graph. Looking at the first pulse only, the input signal starts at a delay of 1 second with an angle of 0. The peak value can also be seen to be at 1.32 seconds and at an angle of 54 degrees. The system settles down at 3.26 seconds with an error of -1 degrees. The error at the end is expected due to the backlash of the gears inside of the NXT motor. I hope this video tutorial was helpful. Thanks for watching.